more about clustering algorithms. But before I do that, I'm going to show you, I have uploaded these 3 papers. This is relating to clustering in meteorological applications. I already talked about that. I'm going to quickly go over the papers just to see how clustering methodology has been applied to analysis of problems in meteorology. So this is one of the simple applications of unsupervised learning to gather information about meteorological questions, meteorologically related questions. So cluster analysis of multi-model ensemble data from SAMX. SAMX was an experiment conducted by NSEP in USA. As I told you, they have 4 models. So I'm going to show you some of the details thereof. Okay, before I go there, Ahmed Al-Hamad, he was my PhD student. He's from Saudi Arabia. He finished it, and he is a professor in a college, in a university near Riyadh. That's me, and Dr. David Stensrud is the meteorologist in question. So it's Al-Hamad is a PhD student in computer science. I'm from computer science, and David Stensrud is from National Space Lab. He's a meteorologist. So it's a combination of computer science and meteorology. And I want to go to the table. I will come to some of the details in a minute. I want to tell you, the region of interest we have is this, the forecast region. I have a model. The model is going to forecast variables in this region. So look at the models in the table. Table 1. CAPS, Center for Advanced Prediction Systems. They have ARCS 4.3.5. They had 5 members with ensemble for that, with differing initial conditions. The NSEP model, ETA model, and there are 25 members. This is how we have labeled the ensemble members to be able to identify who is where and so on. Then the NSEP RSM model, then the National Space Norms MM5 version 2. I'm sure you should all have some idea of what these models are. Some of them, they varied in physics. Almost all of them have different initial conditions. The forecast area, I already told you. The total number of ensemble is 25. They ran this model. They created an ensemble. And what was the question? Question was, do these models have anything similar to each other? How does the difference in physics affect? How does the difference in initial condition affect the solutions? What are the things we are looking for ensemble forecasting? Why do we do ensemble? Because I want to be able to understand, quantify the forecast covariance. That's one of the fundamental questions. So, what the idea? I want to be able to realistically estimate the forecast covariance. I want to be able to realistically estimate the regions in the state space that will be occupied by different solutions, starting from different initial conditions and different physics. That's what I want to find out. That's the idea. Ultimate aim in doing these things. But in general, that's the general point. In here, we are not interested in the variance. We are simply interested in the 25 solutions that's coming out of these 25 different plants to see which of them are similar. Do different physics parameterization lead to similar results or different results? Do the same physics or different initial conditions and parameter setting lead to different results or same results? So those questions were not posed by me. They were posed by the NSEP folks. They ran the experiment, and the data was sitting there. And David Stensrud, my colleague, he said, hey, here's the data, and they are interested in asking several questions. would you have interest in trying to take up this problem? Sure. I had a student whom I had primed already. He has taken many courses and he is ready. Within 2 years, he could finish this project. The University of Oklahoma, generally in the United States, what do? I want to tell you the structure of PhD there, just slightly different from the PhD here, because I did PhD here, like you. I studied here, but I'm working there. In there, after BS, after the first degree in engineering, you have to finish 90 hours for PhD. 3 hours is 1 credit. 90 hours is equivalent to 30 courses. So, after first degree, BS degree in some aspect of engineering or physics or anything, and there's also the following thing. There, engineering is 4 years, physics is 4 years, chemistry is 4 years, economics is 4 years, accounting is 4 years. Here, engineering is 4 years, science is 3 years. I know that because I have a first degree in physics, 3 years. So that everybody is uniform. So you do 4 years, you want to do a PhD, you have to do 90 hours. Of the 90 hours, the first 30 hours can be earned by virtue of being a master's student. Then after master's, you have to earn 60 hours to do a PhD. That 60 hours of the PhD can be earned either 20-40, 30-30. The 20 or 30 are coursework. The rest of it are thesis. The coursework that you are going to do post-masters are very specialized. That could be an independent study with your own advisor. It could be a mathematics course. It is a specific course that you want to do. So once you finish all of those postmasters courses, you are ready on day 1. You get the problem, grind it, keep going. That's the plan there. Of course, in India, it's different. I know the Indian system. I know the Indian system. It has not changed much from my days in the late 60s, early 70s to today. It is patterned after the British-German philosophy, but there, the American philosophy is slightly different. So Ahmed was my PhD student, and look at this now. Now I would like to tell you what are all the field variables we had utilized. Before I go there, I'm sorry. The ensemble consists of 25 members listed in table 1. The outputs that are examined include the mean sea level pressure, 500 geopotential height, 3-hour accumulated precipitation, 250 level hectopascal wind speed, and convective available potential energy. Understand? So each of these fields were distributed in the space. You remember yesterday we talked about the question? Each field is going to be represented by a vector. We wanted to be able to analyze each field, the pressure, the height field, geopotential, convective available geopotential energy, and so on and so forth. So these were the field variables. That were the ensemble. The region of interest was given to you already. Okay, now how many data points are there in the domain? 9,477 points. Yeah, you remember my YAM? There are 25 members. So what is my matrix? 9,477 times 25. For how many field? The sea level pressure 1, 500, 300, 250, convective, 5 fields, and each of these for every 3 hours, up to 72 hours. All of it, man. Now, do you get the idea of the data set? It's a big data. It's a big data. It was done about 10 years ago. 10 years ago. In today's world, it is not too big, but it's really big to be able to do that. So we want to be able to classify how the pressure field changes, how the 500 millibar height changes, 250 millibar height changes, how the cumulative precipitation changes. Are you with me, please? Okay. So it is right in the heart of meteorological applications of the methodology that I talked about in the last class. Does it look similar now? This is exactly what I saw in the last class. So exactly what we saw in the last class. I'm not going to bore you, but you now know what to do. So our aim was to be able to cluster these 25, depending on the similarity measures, depending on various fields at various times. And at that time, we didn't have any standard program available. Mr. Muhammad, he created every piece of the code in Fortran himself. Today, what do you do? Python. I'm not criticizing. So he knew every line in every code. It took about 3 months for him to create the whole code. He's an excellent programmer. I still have a Fortran version if anybody wants I can give you, but I don't think anybody in here reads Fortran. Do you? Probably. If you want, I can do it. But MATLAB has very good programs available today, very common. Even this diagram, he wrote a program to display this as well. Even the graphic packages. I'm just going to thumb through just to see how. Look at this now. After 30 hours, just to give you a feel for it. After 30 hours, 36 hours. So what is our job? Our job is to be able to do all these things and go to Spencer and present it and give challenges. And we have to come back with questions and answers and so on. While we were happy producing the clusters based on the dendrogram, he said the following: we meteorologists are used to reading these kinds of plots. Okay? But he said, why don't you display it so that I can visually see the similarities? My similarity is based on the mathematical concept of similarity. Here he wanted to be able to see, because that's what he was trained at. Meteorologists are extremely good in reading maps. That's what they were trained right from the early days. So he wanted to be able to see the display. So we have different, see, cluster one from ops model, so on and so forth. I don't want to bore you with those details. It's a long paper. Please bear with me. I'll show you and come to an end, and then I'm going to go show you another paper. Okay, now look at this now. Similar diagram, but the height is different. That depends on the field. That depends on the field. In other words, I just wanted to show you that this is, while reasonably good theory, we have applied it successfully to satisfy different questions that might arise from meteorological concepts. Remember, this is the first paper. I have all these papers left in here. I would like each of you, whomever is interested, please talk to Dr. Vivi, and he will be able to provide you copies. The next one I'm going to do is Baldwin monthly weather review. This is again under PhD. Look at that. Development of an automated classification procedure for rainfall system. Okay, rainfall. In the United States, it could be a stratiform, the dull rain over a large region. It could be a line. It could be a cells. In summertime, there are intense cells in a short region. It may rain in one half of the street. It may be dry in the other half of the street. So we wanted to be able to classify the features of various different types of rains to be able to classify. This is again a classification problem. So I'm going to Okay, so what is the general model for the rain? It's called gamma distribution. Rain is a positive quantity. Rain cannot be less than 0. So the standard model for rain is a gamma distribution. Gamma distribution has two parameters, alpha and beta. So what is that we wanted to see? How we can fit the gamma distribution for various different types of rain models. So we estimated alpha beta for stratiform, for cells, for lines. And it turned out that the parameters are very distinct for each of these. So we converted the problem of rainfall classification into a two-dimensional problem, alpha, beta. Alpha refers to the mean, beta is related to the variance. They call it location and dispersion parameters in gamma distribution. So we found out that the range of values that alpha and beta took for different types of rains were very different. We could easily cluster them. And that's one of the, here Mike Baldwin was a meteorology PhD student, and John Kane is a colleague from meteorology. That's myself. Again, we always had a professional meteorologist, myself, and a student to work with. They're all Hamani. Here, Michael Baldwin. Okay, I'm going to show you some results in here. I know there are lots of great data in here. Monsoon, non-monsoon types, and so on and so forth. So rainfall classification. If there is interest, we may adapt a procedure similar to this, perhaps. Similar to this. Okay, say these are typical pictures of rainfall. My friend always used to say, if you are going to give a talk to meteorologist, you should always have some visuals. In computer science, I never used to have visuals. Are you with me? So I'm trying to follow the advice of my good colleague. So these are the data we used. These are the parameter values, the plots of gamma probability density. Let me go back a little bit further. These are the plots of the gamma probability. And again, we did the clustering. You can see the tree structure. This is the comparison. You can see the cluster. Again, so we wanted to talk about an automated classification procedure. So stratiform, cellular, linear. Linear is a line. Cellular means strong, intense thunderstorms. You get an idea. Some of you may have already done similar kind of work, but if you are interested in rainfall classification, this could be one meteorologically related paper that applies the tools from AI. Okay. So in the previous class, I may have sounded more like a mathematician. Now here I'm trying to tell you, no, I wear different hats. Yesterday I was looking like an applied mathematician. Today I'm looking like an applied mathematician working in problems related to meteorology. Are you with me? That's where the thing comes in. Then there is a Nusrat. It's a lady from Dhaka. She did her PhD with me again. And cluster analysis for multimodal ensemble data in New England. There's a temperature distribution. Again, David Stensrud is our collaborator. He had a project just put to summertime temperature distribution in New England. New England is the part of the 13 states in the northwest corner of the United States, up from Washington north of east of Chicago, all the way up to the Canadian border. The Britishers came and occupied it. They called it New England. So we still continue to call it New England for better or worse. They call the native Indians in America as American Indian. I'm called Indian American. So there are various labels, right? Okay. Clustering algorithms. This is the region of the country, northwest, that's Canada, North Atlantic. This is southwest part. Cluster analysis, spatial data. Does it look familiar? So clustering is for real. Clustering should be of interest to meteorologists. I'm giving you examples of this through 3 papers. I know not whether such an analysis has been made for some of the analogs of this to the Indian context. Maybe you can talk to your advisors. And I was told that there's a very finely gridded data for rainfall, the so-called Rajiman data, right? Yes. I have not actually seen it, but I have read about it. Such data, gridded data, is a good starting point for you in order to be able to analyze the spatial distributions, the spatio-temporal evolution from various parts thereof. Okay. One more, without belaboring the issue, I want to tell. Well, clustering confluence and mathematics. This is a talk. There was a talk I gave to the National Silverstrongs lab. This is called tornado detection using empirical orthogonal functions. This is again a detection process. This is done with a master's thesis by Prashant Kakani. Myself and Mike Richmond is my colleague in meteorology. So tornadoes, I'm sure you all know what tornadoes are. Every tornado is measured on various features. There are about 128 features they measure of each tornado. About 128. So that's a table. National Silverstrongs Lab specializes in tornado analysis, prediction, algorithms, and so on. And it is there the Doppler radar based algorithms first came to be. In 1950s, US military had an old radar sitting around, and they donated that to National Silverstrongs Lab. That provides the impetus for them to be able to develop very many Doppler radar based weather tracking algorithms. And they have been doing it since early 1960s. So that's the National Silverstrongs Lab. And they have a ton of detail on tornadoes. And so we took up this master's thesis project. Sorry. Tornadoes are classified into what is called Fujitsu scale 1 to scale 5. Scale 1, I believe the minimum speed is about 80 miles an hour. Scale 5 is about 230 miles an hour. For the first time ever in the continental United States, they measured the highest possible wind in a place which is only 7 miles from my home. We were really treading. We did not know what's going to happen, but fortunately, it stayed away. It stayed away about 7 miles from home. So we had seen it in the TV, and we were fortunate we lucked out. But it has caused tremendous damage and casualty, like human casualties. So all the classification. So they had 2,259 tornado cases. This is the postmortem analysis. And they have actually said how many of them are which scale. Remember, they have already classified them. So we wanted to be able to see whether we can automate that decision process. Now, do you see what I'm talking about now? It's a supervised learning. I already have the data, I already know the properties. I want to be able to develop an algorithm that can replicate the human knowledge by training the data that's So these are the features. I'm sorry, it is not visible here, but in print, I think you can read them. The different features. We talked about histograms of various quantities, and we wanted to again fit some distributions, gamma distribution. We used different methods for measuring the parameters, method of moment, maximal likelihood, generalized method of moments. I do all these things in my class so that I can easily give the project to somebody. Okay. So that's the set of 4 papers. I have other papers related to data assimilation. Because this course is largely in data science and AI aspect of it, I want to confine. And we have all agreed that tomorrow, the second lecture, Friday, we will largely devote it to question answering. As several people have approached with different questions in your own area. So the last hour we will devote to question answering. Now I'm going to go back to where I left in classroom. Any questions on this, please? I hope I have convinced you that what I'm talking about is not a bookish theory, the practical tool. The practical tool that meteorologists can successfully use. Okay, now let's go. Better. Good. Toward the end of the last class, we saw the last slide where we talked about the various scales: nominal scale, ordinal scale, interval scale, and the ratio scale. The algorithms I'm going to be utilizing assume my data is given the ratio scale. Ratio scale means what? I have data that I can add, subtract, multiply, divide, compare, test for equality. Now look at this now. What is the basic thing in computation? You may analyze weather, you may design an airplane, you may do whatever you want. But when you compute at the processor level, what happens? You either add, subtract, multiply, divide, compare, check for equality. That's it. These are called basic operations in computer science. Ratio scale allows you to make all these basic operations. But if you go down interval scale, ordinal scale, nominal scales, many of these operations are inapplicable because of the nature of the data. So in terms of classification, there may be some features that may be ordinal. Some features may be on ratio. Are you in my place? What's an example? The example is this. You get 85, the numerical grade in the final exam. They call it B. Are you with me, please? 90 to 99, 100 is A, 80 to 89 is B, 70 to 79 is C, 60 to 69 is D. Anything below D is useless. It's F. Even for graduate students, even D is useless. Anything below C is useless. We all know that. So what is it we are trying to do? The number 85 has a lot more information. To say I have B, I'm collapsing information. 84, 82, 84 is Borderland 82. But within B, when you map them into B, there's no distinction. There's no distinction. Are you in my place? So sometimes we try to collapse by mapping that loses information. Sometimes we may be able to map the opposite way to be able to see, compare, and so on. Ultimately, truth, false. They are logical quantities. Truth is truth, false is false. I want truth. I also know when certain things are false. But when you say truth is 1, false is 0, then I'm considering a numerical representation of that. If I have a numerical representation, I can then compare. So in data processing, you need to be very careful about the scales in which you measure. how you transform the data to be from one scale to another scale, from numerical scale to letter grade scale, so on and so forth. If there's a lot of information, that's detrimental to analysis. That's detrimental to analysis. Also, then, color of the eye, there's no loss of information. But number grade to letter grade, there's a loss of information. So some transformations are intrinsically lossy, some transformations are not. So you need to worry about this kind of a information lossless transformation to be able to think about what kind of transformation would be suitable in a particular example. So standardized, I already talked about the Z or the standardized, the excess of the standard one, and how Z. We all know the basic Z scores, right? So if I have a random variable X, if I have Z is equal to X minus X bar divided by sigma X. X bar is the mean of X. Oh, thank you. So X bar is the mean of X. Sigma is the standard deviation of X. So whatever be the range of X, the range of Z is always in between 0 and 1. That's one way of transforming. So I can transform the data. Here again, I want you to be able to appreciate. I can do column, I can do row. I cannot do column. Why? The first entry is height, second entry is weight. I can't take the average of height and weight. You have to take the average of quantities that are homogeneous. So what is it we need to do? We need to compute the row averages. We need to compute the rows variance. We have to compute the row standard deviation. Given this group of men, what is the mean? Given this group of people, what is the variance? What is the standard deviation? Because of the unit considerations. So that's what this one is. So here I'm showing an example, the same example I did. This is the raw data, this is the normalized data. I do the same, I apply the same algorithm, you can see the results. Okay, I'm just trying to demonstrate the impact of scaling. In this particular case, the scaling does not have much effect. The results are essentially the same because the magnitude of the numbers here are comparable. Magnitude of the numbers are comparable. Now I want you to think about the following. If I have a vector X, where the first component is 1000, second component is 0.1. If I have vector Y, this is 20, this is 10. And if I'm going to compute the distance between X and Y, alpha place. So what is this distance? This distance is going to be 1000 minus 20 square plus 0.1 minus 10 square summation for that. This guy is much bigger than this, hands down. So he's going to dominate. Everybody plays scales. I'm sure you all know that. And that's the reason. So there are two kinds of scaling. One is non-dimensionalization. Another is scaling itself. In meteorological model, we generally prefer non-dimensionalized versions of the model. Per unit basis, you can do that. Sure. I'm just giving you. Okay. In other cases, I may be want to do the transformation. I may be wanting to do the transformation. Suppose the XOJs are positive, but I want to be able to map it into positive and negative. And you all know logarithmic function. Logarithm of 1 is 0. Logarithm of number between 0 and 1 is minus. Logarithmic function goes like that. So if this is the x, this is log of x. So the values in between 0 and 1 are going to be negative. So if I want to be able to transform a positive quantity into a real number, you can do a logarithmic transformation. If you want to do other way, you can do exponentiation. If you want to convert the positive negative into positive quantity, you can take exponentiation. Sometimes you may want to take the square root. Many a times you want to be able to remove the outlier, and there are very good statistical tests for identifying who the outliers are, and so on. So I'm not going to go into the algorithm for outliers. We already talked about if I have n objects, the number of pairwise resemblance coefficients is n into n minus 1 by 2. Everybody with my place. That many pairs. So Euclidean distance, average Euclidean distance, that's what we talked about in the last class. You remember I also tell that cosine of an angle between the two could be a similarity. Now I'm doing the same problem by changing the measure. Everybody, I'm trying to solve the same problem in every possible way so that you get a handle on the performance of each of these algorithms. And these problems are very simple. And these simple problems will enable you to get a good geometric sense of what the algorithm does. And that's very important to have a thorough understanding. Coefficient. I'm redoing it by correlation. I told you I got another 120 slides. But I used for a course. If I use for a course, these are all homework problems. Hey, I do one method, I give you the basic idea, and I do two methods, simple extensions, as a homework problem for you to be able to redo so that you all have an aha. That way. So I very strongly urge you to download these files and please use MATLAB related programs to be able to test and have a good hands-on training. Okay, good. So hierarchical algorithm is what I'm talking about. So I'm now going to talk about the hierarchical algorithm we talked about is called agglomerative algorithm. Why? Why not? The opposite of it is called division algorithm. So what is the division algorithm? I have a set of objects. I want to throw them into different clusters. I want to divide the set of objects into a small subgroup. That's called division algorithm. The very well-known k-mean algorithm. How many of you have heard of k-mean algorithm? Only one. Yeah, we'll talk about it very quickly. K-mean algorithm is an example of a divisive algorithm. What we have been talking about is called hierarchical algorithm. So begin with the n clusters with one object in each cluster. I'm trying to summarize all the things we have done so far in the form of an algorithm now. Let the clusters be labeled 1 through n. The example I had, n was 5. Initially, I had 5 clusters, 1 for each object. Search for the resemblance matrix. So compute the resemblance matrix. Search for the entry in the resemblance matrix that is the lowest. Everybody, please. Let P and Q be 2 clusters that are similar according to that measure. You remember the first round, 5 was the minimum. How many of you remember that? 5 minimum. It brought 3 and 4 together. 3 is P, 4 is Q. So it brings the 2 clusters, P and Q, together to form a new cluster with 2 objects. So I had originally n clusters. Now I'm going to have n minus 1 clusters, all but 1 having 1 each, only 1 having 2 inside. Now reduce the number of clusters by 1 by merging the 2 clusters P and Q. Label the new cluster. No, now I'm talking about algorithm now. Originally his name was P, his name was Q. I'm going to merge them. What is going to label them? Always label by Q. Let P be less than Q. P is a number, Q is a number, right? If 2 numbers, one must be larger, another must be smaller. Pick Q. What is Q? Q the larger of the 2. So the algorithm knows uniquely how to do that. How many of you are named? When you do the algorithm, you have to make these decisions within the algorithm. So the resulting cluster is called Q. P is gone because P has been merged with Q. Update the resemblance matrix. Here you are going to face a new problem. What is that? Instead of point-to-point distance, you are going to have point-to-set distance. Set to set distance. We already know how to solve those. There are several ways of doing it. One is maximum, another is minimum, another is the average. I prefer the average. Why? Every element has a say in it. Almost all the problems that we have done in my 3 meteorological papers, we always prefer the average. We always prefer the average. So label the new cluster as Q, update the resemblance matrix to reflect the revised similarity between the new cluster Q, the new cluster has been called Q, and the existing clusters other than P, because there's no more P. Delete the row and the column of S that corresponds to the cluster P. P is gone, right? You got to do, you are not doing it in pencil paper, you have to do it in a program. That's what we need to do. Now perform step 2 and 3, a total of n minus 1 times. Each time you are going to grow the clusters. Originally there are n clusters. I continue up until all of them are in one cluster. So what is the total number of iterations that is needed? Okay. So in n iterations, you should be able to do that. And this is the algorithm here program, my student program. MATLAB has a very nice program. Python library has a nice program. R has a nice program. So there are several packages that are available. I would like you to be able to. There are lots of other algorithms. I'm not going to see hierarchical clustering. Now I'm going to talk about, if I talked about all of these, it will take several lectures, but I have already introduced you. I talked about half a dozen different methods for hierarchical clustering. Please take this as a homework assignment, read through, do the problem, enjoy. And if you have any questions, you can always send me an email. I'll be there. If you have a good question, to me, every question is a good question. You'll hear from me. But not until after March 15th, because I'm going to get travel. Good. Now I'm going to go to the next class of ideas. I'm more interested in classes of ideas now. So what is the first class of idea? Centered around similarity or resemblance. With me, my friend had a question this morning. He has used the concept of homogeneity. And the question was, is homogeneity-based clustering algorithm is similar to similarity-based algorithm? Indeed. For an example, we try to group people, Maharashtrian, Telugu, Kannada, Tamil. And what is the classification based on? Their mother tongue. So I'm trying to find the homogeneity among people based on the mother tongue. I can find a homogeneity among people based on the degree. I can find a homogeneity based on the fact that they are married or not. They are working or not. Retired or not. So if you give me, in other words, homogeneity is always across a particular attribute. So he used that kind of analysis, which is very logical. In here, what is that we are trying to do? We are not going to cluster object based on one dimension, like you are Maharashtrian, you are Telugu, you are Tamil. That's based on only one attribute. Here, we are going to base classifications of object based on all attributes. Everybody? Every attribute that you have had that distinguishes you from others is going to dictate which group you are going to be assigned to. Is this homogeneous? Yeah, homogeneous in all these variables. So the concept of homogeneity, the concept of resemblance, the concept of similarity, they are very similar conceptually, but depending on your definition, you can define. Good. Now I'm going to go to the next concept. I'm given a matrix X. So what does this correspond to? I have a n-dimensional space. I have n points in them. So the space is Rm. I have n points in them. The data is given, the data is fixed, the distribution of the data is fixed. If the distribution of the data is fixed means what? Its mean is fixed. Its covariance is fixed. How many of you know how to compute the covariance of X? Come on, guys. That's a problem in basic statistics. You should know. That's not a job of AI. That's a prerequisite that comes from probability, knowing probability theory and statistics. You cannot do AI without good prerequisites. What are the prerequisites needed for doing good AI? Good experience in calculus, especially multivariate calculus, a good experience in matrix theory, a good experience in probability theory, a good experience in statistics, and a good ability to numerically do things. All of you, why am I mentioning this? I want each of you to calibrate yourself. Don't let anybody else calibrate you. You calibrate yourself. How good is my probability theory background, statistics background, numerical programming, numerical analysis background? The better you are in all these things, the faster you can catch up on the applications. So AI is an application that requires all these tools and techniques. So I can compute the mean, I can compute the covariance matrix, and the trace of the covariance matrix is equal to the sum. So let me call the covariance under sigma R. The covariance matrix R, the trace of R is equal to summation RII, I is equal to 1Tn. Everybody please? The sum of the diagonal elements. Every diagonal element in the covariance matrix is a variance. The sum of the variance is called the total variance. So given a set of distribution of n object, the total variance is fixed. You can't change it. How many of you have made? In data analysis, if you change the data, you go to jail. Your job is to analyze the data, but not to change the data. So what is the thing that are fixed? Given a data, its variance is fixed. How do you compute the total variance in the given data? You compute the mean, you compute the covariance matrix, you compute the sum of the diagonal elements of the covariance matrix, that is fixed. All of you? So the aim in data analysis is to be able to explain this observed variance. Okay, that's a fundamental thing I want you to remember. So if I cluster the given data into different clusters, each cluster will have its own mean M1, M2, M3, R1, R2, R3. Everybody with me, please. So this is called intra-cluster scatter. Variance refers to the scatter. Are you with me? If I have a normal distribution, if I have a unit variance, it comes like this. If I have a normal distribution with variance 10, like this. The tail of the normal distribution with variance 10 is much thicker than the tail of the normal distribution with variance 1. The tail is thicker than means 1. The probability of seeing larger values is small. All of them. So the variance relates to the distribution, and it tells you the expansiveness of the realization that one can have. And that's what's called a scatter. How much the data is scattered. So what is the fundamental theorem? I'm not going to prove it, but this is the fundamental theorem in data analysis. Given the total scatter as measured by the variance, the total scatter must be the sum of the intra-cluster scatter plus the inter-cluster scatter. So you can consider this as one object. You can consider this as another object. You can consider another object. If there is only one object, the variance is 0, because he himself is the mean. To compute the variance, you have to subtract the mean. So one object has one number has no variance. If I have two numbers, that's a variance. I have a mean, I have a variance. Everybody plays. So if more than one name, that's a variance, that's a scatter. So what is the conservation theorem? the total scatter in a given data is the sum of the intra-cluster scatter plus the inter-cluster scatter. So by minimizing the intra-cluster scatter, means what? I'm trying to make these clusters as tight as possible. Yeah, I want to have a cluster which is very tight. So because the total sum is constant, by minimizing the intra means within, by minimizing the intra-cluster scatter, I'm trying to maximize the inter-cluster scatter. Inter-cluster scatter means what? Between. That means I'm trying to make the balls as tight as possible while pulling them out as much as possible so that I can hope to get non-overlapping clusters. So what is the difficulty in clustering? To see whether there is overlap. All of you? There could be overlap. So what is one of the aims in clustering? The aims in clustering is you cannot change the variance that is given to you. You cannot change the distribution that is given to you. You are only allowed to group them. The total variance is fixed. You are going to divvy up the variance into two groups. One is the sum of the inter-cluster, the sum of the inter-cluster and the sum of the intra-cluster. If the sum of two quantities is fixed, I can minimize one by maximizing the other. Everybody with me, please? That's the basic philosophy in clustering. So there is a second class of method for hierarchical clustering that tries to exploit this property, and that's called Ward's algorithm. Ward's minimum variance clustering method. That's what I'm going to talk about now. Now, do you see philosophically there is a difference? In the earlier case, what is it we did? I'm looking for similarities based on attributes, based on correlation, based on cosine of the angle, based on the distance. That's one class of ideas, resemblance coefficient based ideas. By exploiting this fundamental theorem that I finished talking about, Ward, being a statistician, he came up with a new algorithm. So what did he say? When you bring objects together, originally, individually, n objects were by themselves. So intra-cluster variance is 0 because there's only one. You need, for comparison, you need two people, right? She got a better grade than him. I can take the average of the grade. That's the variance of the grade. Are you remembering? So what is the idea here? What's proposed? I want to bring in two objects together. When you bring in two objects together, the variance is going to increase. Which two objects, if I pair together, will result in the minimum increase in the variance? Are you all with me? How many of you are with me? That's a wonderful idea. To me, I know you're all very bright people, otherwise you wouldn't be here. Otherwise, IITM would not have hired you for a PhD. So what is that I'm going to emphasize? What is the easy way for me? I could have given you an algorithm. In which case I consider as a cheating. Are you with me? You are capable of producing your own programs. What is needed? Ideas. Yes, for large problems, sometimes you may have to, it'll take 7 days to make a program, in which case you can demonstrate a few things using an algorithm. I'm not opposed to giving programs. But if you're interested in learning something new from a starting point of view, always emphasize the fundamental principles. Because once you have the fundamental principle, remember the case of Al-Hamad. So what's the fundamental idea? If each objects are themselves in one cluster, the individual variance is 0. In that case, the total intra-cluster variance is 0. all the variance is essentially intercluster. I want to decrease one by increasing the other. Increasing the other means I have to bring two people together. You bring any two people together, there's going to be an increase in variance. Variance is a scalar. If you do different pairs, there are going to be different increases. So what's the question to ask? Which pair, if I brought together, leads to the least increase in the variance? The least increase in the variance essentially tells you by bringing them together, I can create a cluster which is as tight as possible. Because variance is the measure of the strength. As I gave you the example of normal distribution with unit variance as variance is 10. All of you? That's a bit basically. So I'm going to bring two objects together. Then there will be n minus 1 single objects, one object with two. Then what is the next one to talk about? Do I add one to the two, or do I bring any other two? You remember what happened in the previous game? I brought 3 and 4 together. Then 1 and 5 came together. Then 2. And 2 I was able to join with 3 and 4. That's the image I want you to have. So 1 and 4, the 3 and 4 I brought together not because of the variance, but because of the distance. 2 and 5, 1 and 5 I brought together not because of the variance, but because of the distance. Here, I want to be able to find out which pair should I bring to increase the variance by the least amount. Is that concept clear? That's what we will implement. I have a whole slew of slides. There are several calculations to make, and we will go over them after the break. Any questions before the break, please? Thank you all. We will meet sharp at 11:30. Thank you. Thank you.
Example.
Okay.
Is it the distance of point?
That's 1 point. What do you see? Let's take the number 10.
भैया कर दिया ना बहुत सॉरी okay smart boy I should have brought my workbooks I have my workbook
You need.
but कहाँ charge करेगा
I didn't bring the.
okay it's okay anyway it's fine
Still it was not running. But now it is not.
it was running and that's good
Even HPC people tried it didn't work.
what
In night it worked.
what why this water is having some bias issues or what
Doesn't want me to do work.
proper
Yeah.
Scaling.
I delete the Windows documents.
I find that
Yesterday I got an 82 view and
Top, right?
yeah.
In some geoscience from
Yeah.
US,
Yeah.
they'll give you
No.
hotel accommodation.
But Saturday, Saturday. Saturday तो घर में रहेगा.
कल मेल आ रहा है.
Morning में तो
Talk.
okay.
Invited talk.
हाँ हाँ.
You also got it? Yes. I said, I'm not interested.
ऑस्ट्रेलिया का होगा 14th फरवरी आपका सुष्मिता मैडम का भी
Thank you. That's it. Which department are you working in?
That's a monsoon mission.
Huh?
Monsoon mission. We are doing with seasonal prediction and estimate prediction in model section. The CFS was in
How long have you been?
yes for 29 years.
Okay.
I'm from India.
I don't know.
No, sir, from West Bengal.
Yes.
I am actually teaching actually attracts me actually. I wish to have all the lectures, but there are other official
We all have a,
official ones, so you have to attend those.
that I call it occupational hazard. Glad to have you.
Yeah, thank you.
Yeah, it's 11:30. We'll start. I gave you the basic idea of what's minimum variance. So what is the first step? I have 5 objects. Each object is represented by 2 coordinates. First object is located at 10, 5. So what is the variance of that? There is only one object, even though the representation is a vector. What is the average of the first coordinate? What is the average of the second coordinate? You subtract the average, you square the difference. That's the measure of the variance. Therefore, the total, what is E? The total intra-cluster variance, increase in variance is 0. That means the starting point is E is 0. Because each object, they are themselves in one cluster, so the total net variance among them is 0. Now, I would like to bring in pairs together. So there are 5 objects. How many pairs are possible among 5? 5C2. So 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. So if I want to bring 1, 2, are you with me? I have to compute the average. I have to compute the difference squares. I have to compute the increase in the variance. So what is the minimum that occurs? 12.5. And where does it occur? 3, 4. Aha. 3, 4 were close in, if I looked at it from that way, 3, 4 are close looking at it this way. Here's an idea. Suppose you don't know what the truth is. You are only given detail. You have to find out what the true classification is all about. Can you just do it by one method and then say, this is it, take it or leave it? No. If you write a paper, it will come back faster than it went. with a big R on the top of it. So you have to, so what is that you have to do? You have to provide an evidence that you have come very close to the truth, if not the truth itself. Are you with me? So how do you do that? If different methods coming from different methodologies, coming from different ideas, they all converge to similar conclusions, then that similarity in conclusion is probably close to the truth. Are you with me? That's how you have to convince yourself, the reviewers. I don't know the truth, neither you do, but I'm going to provide you from multiple angles such that the truth doesn't escape my argument. Are you with me? That's right. So what is the idea here? Don't stick to one method. Look at all possible ways. Does every road lead to Rome? Are you with me? If every road leads to Rome, then you have found the truth. And that's the idea I want to impart at this stage. So, by merging 3 and 4, gives the least value of E. E was 0, now E is going to increase by 12.5. 12.5. Earlier, what is the similarity between 4 and 3? If you remember 5, she asked the question, how did you get the threshold yesterday? You remember?
Yeah.
So that's one attribute. This is another attribute. So I'm now going to bring 3 and 4 together. I'm showing the calculations now. So there are 2 coordinates, x average is the x coordinate, average is the y coordinate. Everybody?
Yes.
So I now talked about the next thing. So I have already, so this is the next step. Now I would like to be able to, so I have done 3 and 4 together. I had 5 objects, now only 4 objects. 3 and 4 together, 1, 2, 5 are remaining. So I have to ask myself the question, do I put 1 with 2, 1 with 5, or 1 with 3, 4? Everybody, please?
Yes.
All possible combinations. And that gives rise to, say, cluster 1, 2. So I'm just trying to show you different combinations, the calculations there are. So look at this now. So now let's look at this now. This is the second step, step 2. I already have 3, 4. On the top of 3, 4, I could have 1, 2, 1, 5. I could have 2, 5. Or I could have 1, 3, 4, 2, 2, 3, 4, 1, 3, 4, 5, 1. All possible. In other words, who is going to be, which cluster I'm going to have to be brought together. So here again, the net increase is 37.5. Everybody please. The calculation. So there's a combinatorial problem here. Are you with me? But you have to do that. You can easily do that. So long as the number of objects is not too big. So, are you with me? That's right. So computationally, it could be a little demanding. There, the computationally is not as much in demand. It's slightly simpler, but that's based on one philosophy. This is based on another philosophy. If 2 philosophies starting from distinct point come to similar conclusions, then we have something closer to the truth. Now the next step. 2, 3, 4, 1, 5, 1, 2, 4, 3, 4, 1, 3, 4, 5, 2. Again, the minimum is, you all know what the blue line is all about. I'm showing all the calculations in here for you to be able to verify. Now I got that. Okay, now the height of the dendrogram is different because I'm talking about different methods. But the ideology, once I get the histogram, I'm sorry, dendrogram, which is the tree diagram, is essentially the same. So this tells you the tolerance. With me? So you can really see 1, 5, 3, 4, 2. As I go up means what? I'm trying to be tolerant of the differences. Life is full of compromise. Compromise means tolerance. Are you with me? So to be able to tolerate the differences, and that gives you the nested sequence of clusters. In this particular case, it turns out the trees are identical. In this particular, it turns out the trees are identical by many methods. Standardizing, transformation, I have already talked about, and various other principles of clustering. How many have heard me? Then there are graph theory based algorithms, which I'm not going to talk about. I'm going to leave it to you once I get you started. You can see the graph theory based algorithm has a slightly different take on that. Now I want to come to the opposite aspect of it, which is called partitional clustering, hierarchical clustering, partitional clustering. In partitional clustering, what's the idea? First, you need to divide the given set of objects into K subgroups. What's the value of K? Arutme? You don't have any idea. So what did you first do? The hierarchical clustering is always exploratory. Hierarchical clustering essentially tells you I can have either 2 or 3. If it is 2, 2, 3, 4 in one cluster, 1, 5 in another cluster. If it is 3, 1, 5, 4, 3, and 2, 3 clusters. So what does this tell you? I don't know the precise answer, but the total number of clusters is either 2 or 3. All of it may?
Yes.
Therefore, hierarchical clustering is always used as a first step, as a first exploratory data analysis to examine the underlying similarity, to extract the underlying similarity in the objects. How many of it may? Once I know that, then I want to redo. So how can I redo that? So once I said there are 2 clusters, in order to be able to build the cluster, I need a cluster center, a nucleus. How do you identify the nucleus? All of it may?
Yes.
The nucleus could be, that's where the k-mean algorithm comes up. So k-mean algorithm assumes you already know the value of k. Nobody is going to give you, if somebody gives you the value of k, don't believe. You need to be able to analyze by applying the hierarchical algorithm, and you may not get a unique answer. You may get 2, 3 different values of k. For each k, you need to analyze. So let us pretend I have a value of k. Now you know how to attain the value of k. So I need to now create cluster centers. So let me again give you the basic idea of that. The cluster centers are the nuclei. Once I fix the cluster centers, then what do? I need to bring in all the other objects and see to which cluster center this guy is nearest to 2. That's called nearest neighbor classification. So there are 2 questions to answer here. First one is, how do you decide the cluster centers? Second, how do you assign each member to different centers, different clusters? How do you classify? You got the idea? Very simple ideas. Very simple ideas. So what is K? K is the number of cluster centers. K is the number of cluster centers. So what is the statement of the partial problem? So that's what's called the initial seed point. What is seed? The seed is the nucleus of each cluster. So I'm going to define the algorithm at high level. Choose first K objects in the data set. So how are you going to create the nucleus? Are you made the centers? One way would be just randomly pick K objects. Label the objects from 1 to n. Are you made? So K is already fixed. And choose those labeled n by k, 2n by k, k minus 1 by k, and n. In other words, I'm trying to divide the numbers 1 to n as k by n by k. N is a larger number, k is a smaller number. I'm assuming n is divisible by k, so n by k is an integer. So I'm going to pick the set of integers from 1 to n with a spacing of k in between them. So subjectively choose any k object from the data set. Label the object from 1 to n and choose the object corresponding to the k different random numbers in the range 1 to n. So there's lots of ways to talk about how to get the seed point. So these are all different methods. So what is the first method? You can pick any k data points. What is the second method? And each object is labeled 1 through n. You choose the object n over k, 2n over k, 3n over k, k minus n over k, n minus 1, I'm sorry, k minus K minus 1 times n by k. That's right. And yeah. So first is arbitrary k. Second, those there are multiples n by k, multiples of n by k. Third one, subjectively choose any k object from the set, which is very similar to. So first one says first k object. Subjectively choose anything. The fourth way would be 1 to n are the labels of now of numbers. Randomly choose. You randomly choose k different random numbers from 1 to n. Or take any desired partition of objects into k mutually exclusive clusters and compute the cluster centroid as seed points. The last one, how can you employ that? I have already done a hierarchical clustering. I already know the clusters. Now, compute the cluster centers for that, throw everything else. Now I have cluster centers, they are the seeds. How many of it me? So that starting seed, you can start with one of many. Come on, guys, how many of it me? So this is the selection of seed points. I need k seeds. I need k seeds. Is there anything better than the other? My choice would be the last one. My choice would be to bank on my already made analysis, which is the hierarchical clustering. I already know the clusters. Each cluster I have identified, compute the cluster centers, throw them out. So the cluster centers form the seed. Then I have to now regroup them, the n objects, with respect to the chosen k cluster nucleus or centers or seed points. Now, you can do the algorithm by varying the seed, the choice of seed. Maybe you may have to do it by all the methods. Maybe you have to do it by all the methods.
So,
Along with me, this is simply the choice of seed point. Yeah, go ahead.
That you are doing subjectively, say, so different people are doing, say, different choices.
If different
So
people are doing
results, will it be more converging or it will be different?
I want to find the truth. I want to be find it in whichever possible way. Anyway,
May not be exactly
not
everybody,
exactly the same, but what?
but
They're
very
not,
close.
answer not unique for this one.
But they can come very close.
That's what. Now, but I don't know the truth. But you and I found something very similar. Then it's not, each of us may not know the exact truth, but we are not too far from the truth.
We're close to it.
Yeah. Exactly. You have a question?
Similar to.
Answer?
But one more, sir, like if you are subjectively taking, we might end up in different results also. No?
That's possible. That's possible. That's why you can. So I'm not saying do it by all the methods. One method is preferable than the other. Why? But always conditioning on the previous knowledge is always the best method. So these are the general things generally you will find in the literature. But my choice would be either I'll pick them randomly or I pick them with choice 5. Because I already have done work and I would like to be able to exploit the knowledge I have already gained. With me? I'm not saying you should follow exactly this. You have to choose the one that makes a lot of sense to you. The last one, to me, make a lot of sense because it is conditioned on an analysis I have already done. It is not, there is nothing random about it. So now then the initial partition. You see, I'm done with the seed points. Now I'm going to talk about the initial partition. Assign each object to the cluster built around the nearest seed point. This point remains stationary throughout one full pass over all objects. In other words, I have cluster centers which are fixed. An object comes in. You throw him into the cluster whom he is nearest to. So in that process, each cluster size vary. During that process, you have two choices. Either you can update the new seed point or keep the old seed point. Everybody with me, please. One choice is going to keep the old seed points. Hey, these are all ideas. That's what. So let each seed point from the cluster, let each seed point to form a cluster of one member, then assign object one at a time to the cluster with the nearest centroid. After an object is assigned to the cluster, I can update the centroid so that it is the true mean vector for all the objects currently in that cluster. So that's the second alternative. First one says that you keep the centroid fixed, you keep assigning. While you keep assigning, the population of different clusters increase. You have a choice to either update the seed or not, don't update the seed. That's one way. Second one says update the seed. Because the thing grows. Use hierarchical clustering to obtain initial partition. I have already talked about that. So this is what is called creating an initial partition. What are the different ways of doing it? The analyst could use his judgment to sort the set of objects into the initial partition. Are you with me? That's right. So the analyst could rely on the same random allocation scheme. The random allocation is the random choice of seed points. So I'm talking about all possibilities. So when you create an algorithm, I don't want to create one algorithm. There are lots of decision processes. So you are considering a tree of choices. Everybody? That's right. Tree of choice. Tree of choice. Now I chosen the initial points. I have chosen the initial partition. Everybody? Now I want to talk about a criteria for partitional clustering. So what is the criteria for partitional clustering? I am given the original matrix m by n. The problem is to partition X into k clusters. The clusters are such that the union of all the clusters is X, and no two clusters have anything in common. Overlapping, non-overlapping clusters. Everybody. Such that the sum of all the elements in one cluster is the Ni, the ith cluster, and the sum of all the elements, summation Ni is N. How many have I made? I have divided them into clusters. There are k clusters. The clusters are non-overlapping. And that's the mathematical characterization of that initial. Now, I'm going to use the criteria. Until now, in the hierarchical clustering, I did not work for optimality. I let things take care of themselves based on the increase in variance or minimum distance or maximum similarity. Are you with me, please? So that's one criteria. Now, on the top of it, I'm going to bring in another criteria. What are the criteria? I have an initial clustering, but I should have the ability to rearrange objects. When I try to rearrange objects, what criteria you are going to have to use to make the clusters as tight as possible, to make them as far as possible. That's one of the considerations in partitional clustering. Okay, please understand. I want to be able to create as many non-overlapping clusters as possible. Is it possible all the time? Cannot be. So in that case, I would like to be able to reassign to see how I can change my initial partition based on certain criteria. When I want to change you from this group to another group, I should have a reason, right? So I'm now going to concoct a reason to be able to do that. One reason is sum of squared error criterion. So the centroid of the cluster Ci is the average of the vectors of the elements that come in that cluster. So xi's are vectors. So look at this now. X star j is the jth column. I'm looking at X star j belonging to cluster Ci. So it looks a little blurred. So let me tell you what it is in terms of, so that you understand what's going on there. So Mi, the centroid of the is the Ni. J, X star J belongs to Ci. So this is the column. Please understand, in matrix theory, we have the following notation. X is a matrix. X star J is the column J. Xi star is the row. Ith row, jth column. Jth column means the second index is same. Row means the first index is same. So Xi star means ith row. X star J means jth column. The columns are objects. Therefore, it is the sum of all the vectors of elements in the ith divided by the number of elements. So that's the centroid in I. Now, I'm going to consider the square criterion Ji for the cluster of Ci. It's a sum of the squared Euclidean distance between each object and the cluster centroid. And what is that? That's a measure of the variance. Everybody with me, please? You subtract the mean, you square the difference, you take the average. What is that called? It's a sample estimate of the variance, covariance. So in this case, so this is a vector, that's a vector. This is an inner product. I hope you all remember that if A is a vector, B is a vector, there are two operations I can perform. One is the inner product, which is A transpose B, which is equal to summation AI BI. There's another one, AB transpose. That's called outer product. This is called the inner product. This is called outer product. What is that? 1, 2, 3, 4. I will do the letters now. Alpha, beta, gamma, X, Y, Z. Are you with me, please? And what is that? That is equal to alpha X, alpha Y, alpha Z, beta X, beta Y, beta Z, gamma X, gamma Y, gamma Z. That's called outer product. That's called the inner product. So this is the inner product of two vectors. Inner product produces a scalar. Outer product produces the matrix. I'm interested in minimization. I only know how to minimize scalars. Every objective function has to be of a scalar type. So what is the Ji? Ji is a measure. I don't have a normalization. If I have a normalization, it will correspond to the total variance. So there is something proportional to the variance. That's what Ji is. You get the meaning of that, please, everybody? So each cluster I can associate the number Ji with that. So the square error of Je for the entire clustering containing K clusters is the sum of the square errors of the individual clusters. Je is equal to sum of all the Jis, I running from 1 to K. So this is one measure that characterizes the behavior, mathematical behavior of the clusters. Everybody, come on, guys.
Yes.
I want you to understand. In India, how do we respond to people? We say, yes. Did you say that? Come on, guys. Please look into the mirror when you say that. I used to say that when I went to USA. My mentor, Faraham, stop. In America, yes, no. But you keep saying like this. All of me? Have you seen? That's right. So sometimes people laugh like that. So I don't know whether it's yes or no. Maybe a linear combination is yes or no. So please respond. So when I say, so I can ask you, are you with me? Just to get a feedback, just to be able to, just to be able to.
Yes.
Yes.
That's right. Yeah. No, that's right. So, so this is, until now, I based everything on simple intuitions. Now I'm trying to bring in some mathematical ways to characterize the quality of clusters. With me?
Yes.
The quality of clusters. So JI is the measure of the spread. JE is the total measure of the spread. We know the conservation principles. Are you with me? So what is one way to think of it? Where am I going now? Can I, so I have an original assignment of objects. Can I change the membership of objects such that I can decrease some quantity? What is I want to decrease? The JIs. Are you with me?
Yes, sir.
That's right. So if you get the basic idea, you can do it. Every one of you, if I give you 2 hours, you can come up with an algorithm. So that's why I'm not giving you an algorithm. I always give the mathematical argument first. The algorithm follows readily. I don't have to even spend a lot of time on that. So that's what's called sum of squared error criteria. So how are we? So what is it we have done? Given K clusters, we now know how to compute the total sum of squared errors. Everybody? How am I going to use this? How am I going to use this to be able to embellish the members of the clusters? That's the next question. That's the next question. So the sum of the square error criterion is what we are after. Second criterion is the scatter matrix criterion. You remember the one I already alluded to when I talked about the Ward's method? Come on, guys, the total scatter is fixed. The scatter refers to the spread. So now I'm coming to the scatter matrix criteria. I'm talking about the criteria now. J is one criteria, it's total make the scatter is another criteria. So Mi is the center for each cluster. Yum is the global mean of all the clusters. Because I have a set of n points. It has a centroid, right? So Yum is a global centroid. Mi's are the centroids of the ith clusters. So define the scatter matrix of the ith cluster. What is that? Look at all the columns that belongs to Ci, because I'm interested in SI. SI is the cluster matrix for the ith cluster. Mi is a vector. X star j is a vector. This is the column, that is the row. That's the outer product matrix. That's the matrix of this time. Earlier, I used the inner product to get a scalar criterion. Now I'm using outer product to get a matrix-based criterion. Do you see the difference, please? That's right.
Yes.
That's right. So I know how to compute the mean. I know how to compute the scalar matrix. The total error criterion is inner product. Total scatter criterion is outer product. What do you mean? Outer product, inner product, 2 operations in matrix theory. So I'm going to bring the concept from matrix theory to be able to create quantities of interest in partitioning. Are you with me? That's right. So this is what I want to tell you. So whenever you are doing something, you have to be able to tell the following. This fact is meteorological. This fact is oceanography. This fact is thermodynamics. This fact is momentum. This fact is mathematics. This fact is probability theory. That fact is statistics. This fact is numerical analysis. You should be able to apportion which part comes from where to make the whole. Then you know how the whole should be made. So pull it to pieces, and then you can rebuild it very easily by associating which argument is mathematical, which argument is physical. What is me? Sometimes it's confusing between all the things is what matters because it causes confusion. Okay, now, so what is the total within scatter matrix is? Sum of all the SIs. So SI tells you is the measure of the scatter within each cluster. There are K such matrices. The sum of the K matrices is SW. So this is the total within cluster scatter. That's called intra. Intra means between, within. In between cluster matrix SB, B is between
So what is that? MI is the global mean. M is the global mean. MI is the mean of the individual objects. In each of these, there are NI objects. You multiply that by NI, you get the total. You get the total between cluster scatter. So look at this. This is the NI. This is the column. That's a row. Outer product. Outer product. This is weighted by the number of elements in that. So this is SB. So the total cluster ST is defined by that. All of it, me, please. All talked about. I'm trying to quantify each of these things.
Now, are you transposing this?
Excuse me.
Are you transposing that while you're doing for T?
T is the
Transpose.
So like here, sir. This is A transpose B. This is A B transpose. Inner product, outer product. With me. One creates a scalar, another creates a matrix. Now, I only know how to optimize a scalar. I don't know how to optimize a matrix. So I need to create a scalar from a matrix. How many different scalars I can associate with a matrix? Determinant is a scalar. Trace is a scalar. Maximum eigenvalue is a scalar. Minimum eigenvalue is a scalar. Average eigenvalue is a scalar. Everybody different ways. So given matrix has several measures that are associated with which are scalars. So what is the particular thing I want? Scatter by its very definition, the diagonal elements are proportional to the variance. I already seen in data analysis, your job is to be able to explain the observed variance. You cannot change the total variance. Changing the total variance is equal to changing the data, which is a no-no. Are you with me? So I'm now going to consider the trace of SW. SW is the sum of various matrices. So it's the sum of the traces of the individual matrices over K. I can explicitly compute the trace as an inner product. Let's look at this now. Let's look at this now. I'll give you this example. Yeah, this example is very useful. What is the trace of this matrix? Is equal to AX, alpha X, beta Y, that's equal to A transpose B. Alpha may, yes. Given two vectors AB, A transpose B, AB transpose is a matrix. The trace of AB transpose is A transpose B. And that's exactly what is used in here. That's exactly what is used in here. Therefore, the trace of the total can be explicitly written like that. Now, this trace of SW, I can use this as a criterion JE. Are you with me, please? That's right. That's right. Therefore, minimizing the trace of SW implies maximizing the between. Bless you. Do you remember the Watts criterion I talked about? I'm trying to mathematically express all these quantities. So that I intuitively presented the idea in the previous talk. I'm trying to quantify them, giving some life by computing the associated matrices and quantities so that you can compute them and write an algorithm. How many of you have me? That's right. That's right. So I have developed so look at this now. I want to have initial partition. I now know seek points, initial partition, criteria. I have two criteria. Are these the only two? No, you can generate your own. Now actual partitional clustering. How do you use these criteria to be able to do what you want to do? So in this case, what is that I'm achieving? I'm not simply taking what my algorithm gives. I'm trying to do something on the top of it. What is that something on the top of it? I did a hierarchical clustering. I estimated the value of K. I now have total freedom. Originally, I didn't have any knowledge. Now I have a knowledge about K. I want to utilize other information to bring to bear by making the clusters as tight as possible and the clusters to be as far as possible. How can I achieve that? Are you all with me? Where we are? That's right. That's right. Okay, now the algorithm. One of the first algorithm is called Froggy's algorithm. Begin with any desired initial partition. Go to step 2 if beginning with the set of seed points. Go to step 3 if beginning with the partition of the objects. I already have either seed points or partition of the object. Allocate each point to the cluster with the nearest seed point. Seed points remain fixed the full cycle. You have already talked about that. I'm trying to reinforce that. Compute the neat seed point as a centroid of each cluster. Repeat step 2 and 3 until no object is left behind. Everybody is in some cluster. Are you with me? This way I already know. This way I already know. For the sake of completeness, I'm doing this now. McCain's k-means algorithm. So the previous algorithm is a very simple algorithm we already talked about. Now, first, take the first k objects. Again, you don't need to take this. You can do several methods. I already talked about that. So McCain's algorithm suggests this possibility. Assign the n-1 n-k object to the cluster of the nearest centroid. Recompute the centroid gaining the cluster after each assignment. After all the objects have been assigned in step 2, take the existing cluster centroid as fixed seed points and make one more pass. Look at that now. So you first take k points as a cluster point. Assign everybody by the nearest variable rule. After you assigned, you have clusters. You can compute the mean. Then use that as the new seed. Throw away all the objects there. Then redo the nearest neighbor. Are you all with me, please? I want you to know there are as many ideas as the number of people who have worked on it. Before you create a new one, please make sure that you have already looked at the literature. There are books written on clustering and clustering alone. Everybody? Yes. And these are interesting, important because these are directly applicable, as I have already shown you in 3 papers, that meteorology can benefit from applications of these ideas.
This will be an iterative process.
Excuse me?
It will be an iterative process.
And how do you compute? How do you conclude when there is not much of a change? Understand? That's one thing. A convergent version of this method. Begin with the initial partition. So it doesn't say how you do. Begin with some initial partition. You know very much methods. Take each object in a sequence and compute the distances to all the cluster centroid. If the nearest centroid is not one of the object's parent cluster, look at this now. Originally, you start with the initial partition. Initial partition means what? You have already clustered them. For each object in the sequence, compute the distances to all the central clusteroids. So if that I have assigned everybody, you know the centroid of the clusters. Start from object 1 to object n, compute the distance of each object to every centers. If a particular object is not in the nearest place, change it. Or make it tighter, and that's what that one. Repeat the step 2 until the convergence is achieved. All of you in my place?
Yes.
I'm just to provide you different ways of ideas which have been partitioned. The last one, well, third one, I shouldn't say last one. The third one is called squared error clustering algorithms. Squared error clustering algorithms. What's the idea here? Let Y belong to a cluster C. Again, I'm talking about a general idea. I want to decide to move the object Y from, so you can say Y, let Y be the object that belongs to Ci. I'm sorry, it should be Ci. I want to be able to make a decision, should Y continue in Ci or should I change to Cj? As a result of this move, so if I were to move, what's going to happen? The receiving cluster, its mean will change. The sending cluster, its mean will change. Are you there?
Yes.
The receiving cluster, its scatter will change. The sending cluster, its scatter will change. And I need to be able to compute these changes. One is the gain, another is the loss. So, if I'm going to add from Ci to Cj, the old mean of the jth cluster of Mj, its new mean is M star J. I have to update that. Everybody? And the centroid have two, third object comes in, the centroid changes.
Yes.
That's right. And I is losing, so I have to update him as well. So, you remember Ji, Jj, the previous slides, the sum of square error criteria. The receiving one is going to increase, the losing one is going to decrease. So I'm going to update the receiving one from I to J star plus minus. Are you with me? That's right. Now, the transfer Y from I to J only if the decrease is larger than the increase. Are you with me? That's the criteria. The criteria. Are you all with me? Come on, guys. So what is the aim of these exercises? I want you to know that there is no one single idea. There's no one single algorithm. Sometime I want to come back so that you can see me closer. I can also see you closer. So the idea here is that there are very many good important heuristics. Clustering as an object. Clustering is something we do regularly with group, right? So what are the various ideas that we use and how I can mathematically characterize these ideas and how many different possible ways in which I can approach the problem of clustering, the problem of unsupervised classification, the problem of unsupervised learning. Everybody? So I have this is called square error clustering algorithm. I have essentially stated the whole thing in the form of a pseudo code, which you can very easily code it. In MATLAB, there are algorithms that implements this. All of you?
Yes.
That's right. That's right. That's right. So what is the idea here? I originally did something. I was not happy with it. So you have two choices. You originally do something with the hierarchical. You can take it and run away with it. Or you can ask a question. How do I make it tighter? Is there a way I can change things? If I were to change things in the membership, what kind of criterion could I use, should I use? All of it may? These are the basic questions. Why are you here? You should be here, right? Don't we say that? That's right. We partition players. We partition students. We have teams, right? Partitioning. So what are the various ideas we use in doing all these things? Humans are very good in doing these things. So what are the various criteria we would have, or we normally use, and how do I bring it within the scope of an algorithm to be able to classify automatically? Right, that's artificial intelligence, right? To mimic what humans do by an algorithm, to be able to replace what humans have been doing. All of you? You all getting an aha here?
Yes.
Are you getting an aha about unsupervised learning? Nobody's telling you what to do. The data allows itself. I'm letting this data speak. I'm only listening to the data. I'm doing whatever the data steers me through. Okay, now this comes to application, ensemble forecasting. I already talked about it. I'm not going to revisit this issue. I already told you. Remember the SAMX, one of the papers by Ahmed? That's right. That's ensemble forecasting. Application of clustering to any ensemble analysis. When you create ensembles, I want to be able to see how I can use ensemble based on the same model. I can have an ensemble based on multi-models. We already talked about it. I don't want to waste your time on that. Applications to meteorology. These are things that we did about 12 years ago for Ahmed's thesis. And that completes my first oh,
So when sir, you have got that ensemble forecasting, any spread is there means.
I would like somebody to change my name from Lakshmi to Lakshmi. That's right, thank you. So this is a 71-page notes that I got typed. I'm sure there are some typos, but you already, I'm going to give you a copy of this as well. So I have organized them: cluster analysis overview, variables, scales, standardizing data matrix, resemblance coefficient for quantitative variables, basic mathematical facts, data reduction principal component analysis, Fisher's discriminant function, criterion for clustering, the one that we just finished talking about, partitional clustering, combinatorial explosion, that's what I'm going to talk about, iterative methods for classification, hierarchical clustering methods, application of clustering to meteorology. Is about 80 pages of notes. I'm going to give it to you free. Please, what is that I would like to suggest? Print. Write notes, write out some. That's what I do. If I in my days when I was doing PhDs in the late 60s, there was no Xerox machine. I don't know how many of you know that.
Yes.
So we used to go to the library. I used to have a seat in the library for 4 years. That's my seat. We had to go to the library, open the paper, read it, and then write a summary. So for every paper, I did not have a Xerox copy. I had a summary resulting from my own reading of it. Technology changed.
Now, sir, everybody takes photo of
Well,
mobile. They will take.
I'm coming to that. So in those days, I read it. I read all the papers. Now what do? I take copies and then it's an amount of papers. I think I want to read it, so I collect them. I collect more junk than I can really read it. So what do I want you to do? Don't print it, simply collect junk, read it, write your own notes along with it so that it can represent the notes and your own understanding. Please do that. So that's what this is about. And what am I going to be doing here? I want to come to page 54. I'm not going to do it today. I will do it tomorrow, but I want to tell you the question. Is there a notion of an optimal clustering? Hey, we want to do everything optimal, right?
Yes.
That's what engineering and science is all about. Whatever we did, we want to do it in the best possible way. Best means optimal in some sense. So, given n object, is it possible to get the best clusters based on a given set of features? In computer science, we have a problem called, this is an infeasible problem. The number of distinct clusters that you can divide a set of n elements into is exponentially large. To start with, you don't know which cluster is going to be. The number of possibilities, that's a solution space. Are you there?
Yes.
If the solution space is too large, to find an optimal solution, I have to exhaust every possible solution. But the number of possible solutions grows exponentially with n. If the number of distinct possibilities grows exponentially with n, I know what to do, but I don't have time in my life to be able to exhaust all of them. So, theoretically feasible, practically impossible. I don't know whether many of you have seen this kind of thing from computational complexity. So I would like to bring in the notion of computational complexity from computer science consideration. When do I say a problem is solved? When do I say a problem is practically solvable? And all problems that are theoretically solvable can be solved in practice in our lifetime. So partitioning is one such, that's what's called a combinatorial explosion. That means that I just don't know. If there are 10 objects, it could be 1 and 9. All the 10 together. It could be 2 and 8. If it is 2 and 8 means what? Which 2? Which 3? There are so many possibilities. Are you with me? Am I trying to capture your imagination now?
Yes.
One cluster, all of them in one cluster, that's only one answer. 2 clusters. There's one cluster can have 1, the rest of it can have n minus 1. One cluster can have 2, another cluster can have the rest of it. One cluster can k, another one can have n minus k. How do you pick n? How do you pick k items from n items? NCK. Are you there?
Yes.
For every k running from 1 to n. That's the total possibilities of cluster. to give a quick answer to that. That number is so large. If that number is so large, if the solutions, so in order to say I have an optimal solution, what is that you need to do? I need to check everybody to find the best. If you cannot find everybody, if you're only doing a subset of solution, your solution is only suboptimal. Are you making it? Generally in meteorological context, you don't deal with problems of this type. I want to model this, I want to model that, you keep going and so on. But in computer science, there are combinatorial problems which are notorious in terms of being able to acquire time to solve. I know how to do it, but my lifetime may not be enough to do that. Are you making it? I'm going to show you a quick result, and then I will fill the gap tomorrow. First lecture. Yeah, that's right. So there are problems where n is equal to 25. The total number of clusters possible exceeds 4 times 10 to the power of 8. You say, I'm sorry, 18. Sorry. 10 to the power of 18. Is there a number for that? Is there a name for that?
Exactly.
Peta XR.
We have gone to peta. Now it is exact.
We don't have computers except 1 or 2 in the world that can perform exaflops. Are you with me? In other words, clustering as a problem has been solved. Clustering as a problem has been looked at. Clustering, within the context of clustering, the question of optimal clustering becomes important. Mathematically, optimal clustering is possible, but it's infeasible to compute because of the time requirements. Therefore, the solution to any clustering problem, we always settle for suboptimal. Are you with me? Yes. And what is one suboptimal algorithm? Ward's minimum variance algorithm. Ward's minimum. So it only talks about 1 to 2. It doesn't talk about all possible ways, starting from the beginning. Are you with me? So Ward's algorithm is an example of a suboptimal clustering algorithm, but it is good results. So with that, let me stop here. Are there any questions? So tomorrow, what are we going to do? I'm going to talk about the various types of optimization: discrete optimization, continuous optimization, combinatorial optimization problem, explosive nature of combinatorial optimization problem. When do you say a problem can be solved ideally but not practically? What are the constraints from a practical consideration? I'm going to bring in all the computer science related important questions to bear on this particular problem. That's the first lecture. The second lecture is going to be open. I'm going to be ready to answer many of these questions that you may have, and some of you have questions related to data assimilation. It could be related to data science. Please bring back a loaded gun so that you can shoot at me with questions. With me? I would like to know what is bothering you or what is that you want to know about, so I can also learn from it. If I can answer, I will give the answer. If not, I will seek the answer and then communicate. With me? With that, any questions? None? What she was doing with this. Okay, that's all. We are all entitled to do that, right? If there are not any questions, that's our time for the day. Thank you all. Thank you. Again, in my file, I have lots of documents. I would like each of you who are interested in these to be able to copy. Please talk to Dr. Or anybody who can access this.
Some of them. We got some.
You already have that?
Some.
Okay. I have added some more. You may not have a lot of it. Please. So what is the only request I'm having? If you should write a paper based on some of these things, give a reference. Thank you. Thank you. I'll see you tomorrow.
Thanks.
I don't want to. Thank you very much.
Thank you, sir. Thank you very much.
Thank you.